Hi, my name is Ali Abedi. Welcome to our virtual talk at SIGCOMM 2020. This is a joint work with my colleagues Farzan, Mohammad, Omid, and Tim. In this talk, I present WiTAG, our battery-free Wi-Fi backscatter communication system. Many today's IoT devices rely on a battery to communicate with an IoT hub or a Wi-Fi router. Unfortunately, the battery life of these devices is typically from only a few weeks to a few months. Changing the batteries of many IoT devices can be very difficult for the end user, especially because some of these devices are in hard-to-access places. In addition, batteries are pretty expensive. So there are great benefits in designing battery-free communication systems, which make them very attractive for many IoT applications. So, is it possible to get rid of the batteries? The answer is yes. Battery-free wireless communication can be achieved using the backscattering technology. For example, RFIDs utilize backscattering to enable communication between a battery-free tag and an RFID reader. In backscattering communication, a tag reflects the signal coming from a source such as an RFID reader. The tag modulates its data onto the reflected signal. Then, the receiver analyzes the backscatter signal to extract the data transmitted by the tag. The power consumption of these tags is so low that they can harvest their required energy from the wireless signal. Although the RFID technology enables battery-free wireless communication, it relies on readers that are typically bulky and expensive. Instead, can we design a battery-free tag that can be read by Wi-Fi devices? Since Wi-Fi access points are available almost everywhere, researchers have looked at enabling backscatter communication between a Wi-Fi access point and a battery-free tag. However, because Wi-Fi was not designed to work with such tags, Wi-Fi backscatter has become a challenging research problem. In recent years, we have seen several Wi-Fi backscattering systems that try to enable Wi-Fi backscattering on commodity Wi-Fi devices. Unfortunately, all of these systems suffer from one or some of the following problems. Most of these systems require software or hardware modification on existing Wi-Fi access points, or they do not work with encrypted Wi-Fi networks. Some of these systems do not work with modern Wi-Fi standards such as 11AC. And finally, some of these systems have very limited range. In this work, we present WiTAG that enables Wi-Fi backscattering by leveraging frame aggregation in Wi-Fi networks. WiTAG is compatible with all existing Wi-Fi access points, including modern 11AC. WiTAG works with open and encrypted Wi-Fi networks. And finally, WiTAG is battery-free. Before we explain WiTAG, let's quickly review frame aggregation in Wi-Fi networks. A legacy Wi-Fi packet includes a physical header and a MAC protocol data unit, or an MPDU. The MPDU includes a MAC header and a packet payload. Since the 82.11 protocol involves many overheads, such as channel access and acknowledgements, the standard has introduced a frame aggregation feature to improve efficiency. In frame aggregation, we put multiple MPDUs inside a large physical packet called an aggregated MPDU, or AMPDU. We refer to these MPDUs as subframes. Frame aggregation amortizes the overhead over multiple subframes included in an AMPDU. Frame aggregation is now a standard feature on all Wi-Fi devices. Let's review how frame aggregation works in Wi-Fi networks. Suppose that the smartphone has multiple packets to send to the access point. Instead of sending the packets one by one, the phone creates and transmits an aggregated frame. The receiving device, which is an access point in this case, checks to see if the subframes are received correctly with no error. Normally, all of the subframes are transmitted correctly. The access point creates an acknowledgement which contains a bitmap that indicates the fate of each subframe: 1 for successfully received subframes and 0 for the corrupted subframes. Since all subframes were received correctly in this example, the acknowledgement contains 7 ones. When the phone receives the acknowledgement, it can find out the fate of the transmitted subframes. We now explain how WiTAG works. In this example, we have a temperature sensor that wants to transmit its data to a nearby Wi-Fi device. Suppose that the last reading of this sensor is 23 degrees centigrade, which is 0010111 in binary. Let's see how the smartphone can read this data. First, the smartphone transmits an aggregated packet to the access point. When the subframes are being transmitted, the tag embeds its data onto the AMPDU by selectively interfering with some subframes. Specifically, if the tag wants to send 0, it corrupts the subframe by creating interference. On the other hand, to send 1, it does nothing so that the subframe can be transmitted successfully. In this example from the left, the tag corrupts the first 2 subframes to send 2 zeros. Then, it does not corrupt the third subframe to send 1. Next, it corrupts the fourth subframe, and finally, it does not corrupt the last 3 subframes to send 3 ones. When the access point receives this aggregated packet, it finds out that some subframes are not decodable. It then creates an acknowledgement for this packet. Interestingly, the bits in the acknowledgement exactly match the tag's data. When the smartphone receives the acknowledgement, it can extract the tag's data directly from the acknowledgement. The beauty of this approach is that the Wi-Fi access point is not even aware of the procedure we just described. It simply receives an aggregated packet and sends back an acknowledgement which is part of the normal operation of Wi-Fi. As a result, no modification is required on the access point. The smartphone also sends and receives normal Wi-Fi packets. Therefore, it can implement this procedure using a simple app. WiTAG needs to address 2 challenges. First, how can a battery-free tag corrupt subframes? And second, how can a tag synchronize itself with aggregated packets? We now describe the first challenge and our solution. But how can a passive tag create interference for Wi-Fi signals? Isn't the backscatter signal very weak? Let's see how WiTAG solves this challenge. The tag creates interference by reflecting the Wi-Fi signal from the smartphone. To receive an aggregated packet, the access point measures the channel at the beginning of the packet and assumes that the channel remains the same for the duration of the packet. A change, like the reflection from the tag during the packet, can violate this assumption and corrupt a subframe if the reflection is strong enough. To see if the interference from the tag can corrupt a subframe, we calculate the signal quality at the access point, which is defined as the power of the Wi-Fi signal divided by the power of the reflection from the tag plus the power of the noise in the system. This ratio is called SINR, or signal to interference and noise ratio. Now we need to find out if a given SINR is high enough to receive a subframe successfully or the subframe fails. The answer depends on the modulation scheme used by the smartphone to transmit the aggregated packet. Wi-Fi supports different modulation schemes to enable communication in a variety of channel conditions. Each modulation scheme requires a minimum SINR to work correctly, as we show in this example. If the SINR is above the threshold for a given modulation scheme, all packets are transmitted successfully. Otherwise, packets are dropped. Now, consider an example. Suppose that the SINR is 30 dB for a given Wi-Fi packet when there is no tag around. In this case, the 64 QAM works correctly. Now suppose that we introduce a tag. If it can lower the SINR to below 26 dB, which is the minimum SINR required for 64 QAM, it can corrupt the packet. We have done some calculations to show if a tag can actually lower the SINR enough to cause packet corruption. Our calculations show that the SINR depends on the distance between the tag and Wi-Fi devices. We now plot the SINR for different distances between the tag and Wi-Fi client device. The blue line shows the SINR. In this example, the distance between the smartphone and the access point is 12 meters. As you can see, the fate of a subframe depends on the distance between the tag and the Wi-Fi device and the modulation scheme used. For instance, if the 64 QAM modulation is used to transmit the aggregated packet, the tag can crop subframes if it's within 1 meter from one of the two Wi-Fi devices, because the SINR is below 26 dB, which is the minimum required SINR for 64 QAM. As one might expect, the range is limited because the interference from the tag is very small compared to the original Wi-Fi signal. All of our calculations up to this point were based on the assumption that the smartphone and the access point have one antenna. However, most modern Wi-Fi devices support MIMO communication in which concurrent streams of data are transmitted over multiple antennas. MIMO systems suffer from a known problem called noise amplification, in which any noise or interference is amplified by the MIMO system, reducing the SINR. WiTAG takes advantage of this problem and significantly improves its range. Our conservative calculations reveal that a MIMO system amplifies the tag's interference and reduces the SINR by 10 dB. This reduction in SINR means that when the 64 QAM modulation is used, a tag can crop subframes everywhere between the two Wi-Fi devices. We now describe the second challenge and our solution. The second challenge WiTAG needs to address is synchronization. How can a tag synchronize its data with Wi-Fi packets? One way to solve this problem is to find the beginning of the Wi-Fi packet. This way, the tag can find and corrupt the intended subframes successfully. Previous studies have used RF detectors to find and identify the beginning of a Wi-Fi packet. Unfortunately, RF detectors are power hungry. We designed a novel synchronization technique that avoids detecting the beginning of a Wi-Fi packet. Therefore, it does not use power-hungry RF detectors. At a high level, the responsibility of synchronization is moved to the Wi-Fi client device to make the design of the tag simple and low power. The tag periodically transmits blindly without detecting any Wi-Fi packet. The Wi-Fi device keeps track of the tag's messages and tries to send an aggregated packet when the tag wants to send its data. Let's see this procedure in an example. The tag periodically wakes up and tries to send its data. Here we show the tag's message in orange. The smartphone cannot transmit an aggregated packet exactly at that time because of clock drifts and the randomness involved in accessing the channel. Therefore, the smartphone starts transmitting a little earlier than when it expects the tag to wake up. As you can see in this example, the tag's message may not overlap with one of the aggregated frames completely. Therefore, the tag repeats its message a few times. The duration of the aggregated frame and tag's messages are selected in a way that a complete overlap happens with a high probability. Please refer to our paper for more details. We have evaluated the performance of WiTAG under different scenarios. We now present some of these results. In this experiment, we evaluate the performance of WiTAG in a line-of-sight scenario. The two Wi-Fi devices are placed 8 meters apart. The performance of WiTAG is measured at the 7 indicated locations. We first measure the bit error rate of WiTAG at these 7 locations. We observe that WiTAG achieves a low bit error rate, which increases as we move away from the Wi-Fi client device. This measurement is in line with our theoretical calculations that showed the effectiveness of packet corruption decreases when the tag is far from both devices. As expected, the bit error rate decreases when the tag gets closer to the access point. We have also measured the throughput at these locations. The achieved throughput is between 3 and 4 kilobits per second. This experiment shows that WiTAG's range and throughput can enable many IoT applications. We have also conducted a series of non-line-of-sight experiments. This is the floor plan of our experiment setup. The access point is placed at one location and the tag and Wi-Fi client device are moved to different locations. The distance between the tag and the client device is 1 meter. We have measured the bit error rate and throughput at 10 different locations. The experiment shows that WiTAG can achieve a bit error rate of about 1% or lower in all locations. In most locations, the throughput is about 4 kilobits per second, except location J, where the throughput is around 3 kilobits per second. Location J is 18 meters away from the access point and behind a concrete wall. Although the locations we tested in this experiment are behind metal barriers or multiple walls, WiTAG shows a robust performance in all locations. In the next experiment, we evaluate the performance of WiTAG in terms of message success rate under 4 different scenarios. In these experiments, the tag sends its data every 10 seconds, and the experiment length is 17 minutes. In scenario 1, we measure the message success rate when there is a lot of background Wi-Fi traffic on the channel. Despite the busy channel, the tag can successfully deliver all of its packets. In the second scenario, in addition to the background traffic, we add 2 Wi-Fi devices that stream videos from YouTube. Although we inject more traffic, we observe no difference in the message success rate. We repeat these 2 experiments now with 2 tags. The experiment shows that the 2 tags achieve a message success rate of at least 92% despite the very busy wireless channel. In scenarios 2 and 4, we also monitor the video stream to see if WiTAG causes any problem for these clients. We observe no degradation in the quality of videos for any of the 2 clients. This experiment shows that WiTAG can support multiple tags with minimal impact on other devices. In this talk, we presented WiTAG, which enables Wi-Fi backscatter communication by leveraging 82.11 frame aggregation. WiTAG is fully compatible with existing modern Wi-Fi access points without requiring any hardware or software modifications. WiTAG works with encrypted and open Wi-Fi networks. I hope you have enjoyed this talk. Thank you.